All right. Hi, folks. Happy Monday to you. Happy Halloween Eve, as it were. So Ejan sent me a great picture. I'm going to show it. You get full credit. Where did you find this, by the way? Facebook. The scariest picture any of you can ever imagine. P equals 0.06. Even scarier than like broccoli on a pumpkin. That would be my son's worst nightmare. But, yeah. Nice. That requires some effort.
It was like very nicely carved.
Please send that to me. Any fun pictures of pumpkins with stats jokes, please send. I collect these things. So, yes. Yes, indeed. Is anyone going to dress up like anything fun? No, we're not. It's not going to be a thing. Is anyone going to hand out candy, or are you going to like turn up the lights and hide? That's what I did in grad school. It's like, I'm not going to buy other people candy. I can barely afford my own candy. Yes, I will be handing out candy at the Hoffman household. Although Huey tells us now he doesn't want to wear his costume. So we'll see. I know. He was going to be Rubble from Paw Patrol. And he's mad because he wants to be Sky from Paw Patrol because she's the purple one. Purple being his favorite color. Who knows? So yes, my favorite Halloween costume, by the way, was the year I dressed up like my advisor at a grad student Halloween party. I can dig that photo out if any of you want to see it. My then boyfriend at the time dressed up as his wife. We was dressed up as the Ashleys. Actually, this was back in 1999 or so, and he heard about it and insisted on seeing the picture, and luckily he thought it was funny. So that could have gone very wrong, but the funniest part was walking to the party and watching people's heads be like, what? And then, I get it! So those are the fun ones, but not this year. So homework. I've gotten a couple email questions. How's that going? Anyone want to take this opportunity to ask more questions?
It's not a question, but it's a hardware.
The model comparison macro didn't work for you. What did it do?
Actually, I should have some table in the output, right?
Mm-hmm.
But they are empty.
It's empty. Well,
but last time it worked.
Last time it worked. Well, I may have to see your code to troubleshoot that. I can try and help do so. Any other questions on that? No? All right, then let's do a little reviewage. Reviewage being a word I just made up. Not to be confused with sewage. Reviewage. What does a quadratic effective time do? Tells you about acceleration or deceleration. Yes, it makes a predicted trajectory a little bendy. How many kinds of quadratics are there according to my definition? 4. What are they? More positive. There's one. Less negative. Less positive. Ah. More negative, less negative. Yes. So a quadratic does what to the linear slope? How do we talk about the quadratic? Twice. Where does twice show up in the sentence? Remember? I always say it as the first word of my sentence. Twice the quadratic is what? It's how the linear rate of change changes per unit time. That's a mouthful. Twice the quadratic is how the linear rate of change changes per unit time. It gets more positive, less positive, more negative, or less negative. That means that the quadratic itself is half the rate of acceleration or deceleration. You have to multiply it by 2 to get it to be something. So last time we looked at Sas code designed to help interpret what a quadratic is doing, both in terms of how it's creating predicted means and how it's creating predicted slopes. And I wanted to take a minute just to go over that idea to see how those estimate statements, where those come from, because it's not always intuitive. But I think if you can see the math behind it, just the algebra, how it works, that it might make more sense. So let me pull up a quadratic model here. I've got one somewhere in my slides, I'm quite certain. Here's one, slide 17. This is my quadratic model. So which terms are the fixed effects? I will accept either a color or a letter designation. The red things, yes, these are gammas in my notation. Notation is always person specific, so I'm trying to be internally consistent, but they may be called other things in other people's notation. And which are the random terms? The U's, yep. And so if I want to talk about expected values, so expected predicted outcomes or expected slopes, the only thing that is going to be relevant are the fixed effects, because the U's talk about what the prediction would be for each individual person. The way that we tend to interpret models is what it predicts on the aggregate. So if I were to write out, I'll do this in words so that you can all play along here. Predicted outcome at a particular time, right? I'm just doing this shorthand here, would be the fixed intercept gamma 0, 0 plus gamma 1, 0 times that time, gam, there we go, plus gamma 2, 0 times time times time, right? So those are some words. If I want to put that in terms of notation, do you guys know the equation editor in Word, how to get to it? Hit Alt and it equals, and it pops up. Then you can type Y to get subscripts. It's the same keystrokes as in LaTeX, if any of you know that language. You do an underscore, and then whatever you want to be the subscript, and hit the space bar, and it pops up like that. So it's a super fast way of writing things. To do Greek letters, use the slash that's above the enter. Is that forward slash? I've never learned the right words. The one that's above the enter, not the one that's down below by the shift. Like if I type gamma like that and hit space, then it pops into a gamma, which is really cool. Another underscore 0, 0, space to get it to pop into place here. So another gamma, space, underscore 1, 0, space, times time. Time gets a TI, if I'm being complete here, plus gamma, space, underscore 2, 0, space, time, time. All right, there. Go over here. So this is what we would need to figure out what the predicted outcome would be at any time, and also for any person here. So what would we put if I wanted to know what it would be when time equals 5? Well, I take this thing, and I would put a 5 here, not a T, just a 5. And what would I put here? Yeah, either 5 times 5 or 25, as it were, right? So then I would fill in whatever the model said the fixed intercept was, whatever the model output said the fixed linear slope was, and whatever the model said the fixed quadratic slope was. That sentence right here, I'll see if I can show both at the same time, is exactly what this code is doing. Come on. Come on, you can do it. There. In the first 6 estimate statements, I'm asking for a predicted outcome at each occasion, where the last line is what I've written up above. So the word intercept refers to the idea that SAS is going to give me a gamma 0, 0. I need one of those. The word time 1 refers to the fixed linear time slope estimate. I need 5 of those if I'm talking about the predicted value at time equals 5. And the words time by time, that refers to the fixed quadratic slope estimate, and I need 25 of those if I'm talking about time 5. So SAS does the math for you, filling in whatever the gammas happen to be in your particular model for the words that they represent. So when you put time 1 into the equation, you're asking for a fixed linear time slope when you put it in the model line here. When you put time by time in the model line, you're asking for a fixed quadratic slope. It then uses those numbers in building a prediction that's specific to whatever time you've asked for. Okay. With me so far? This is no different than you learned how to do like back in regression or even back in like 8th grade algebra, right? You plug in a value for your x variable, in this case it's time, and you come up with a y based on your linear model. So for instance, if I have a homework question that says something like, what's the model predicted well-being at time 6, right? This should be relevant. Now the other ones, these ones down here are a little trickier. Let me go back up to my equation though. Here's my model for how the linear and quadratic effective time create an expected outcome at any occasion. This next 6 statements are asking about the linear effective time specifically. So I want to pull those out. Does the fixed intercept predict the linear effective time? No, it's not attached to time, so it gets dropped. So what we're looking for here is we'll call this, just use some words here, fixed effective time equals that. So we're going to do some rearrangement here. What I'm actually looking for is what goes in front of the time variable. So if I take this statement, take out time, like that, there. That might make it easier to see. What I'm looking for, if time is this is my linear time variable, I'm looking for this term in front. What is the number that needs to multiply and create my time slope? And it's not just the linear effective time as it would be if that's all that was in the model. It's also the quadratic times time. So that part that's in front of time, that's highlighted right here, that is what these last 6 lines are doing. When I say time, I'm saying the fixed linear time slope. In order to create the linear time slope at any occasion, I need to start with one of those, and I need to add to it a value for which time I want the linear slope to be. So if I'm still at time equals 5 as where I want my prediction, that's this last line here. The only catch is that you have to remember to multiply it by 2, because twice the quadratic is how the linear slope changes per unit time. So why in the estimate statements it's 2 times time down here, whereas it's time squared up here, is because these variables are meaning different things. The first time, I'm having to fill in the value for time twice. The second time, I'm only filling in the value for time once and multiplying it by 2. So these are tricky. I'm not going to lie to you. It takes a little bit to get your head around them. The good news is that once you see it, you can't unsee it. It's like those magic eye pictures, right? Which coincidentally I can't ever see. I've never once seen one. I can't see the sailboat, for instance, in Mallrats. I never got that joke. But I can see this, and ultimately this pays the bills. So questions or any of that you want to hear again? Because we're going to see a whole lot more examples of this use of estimate statements to generate predictions. Not just predicted outcomes, but predicted slopes. Okay. And then let's look at the example that we were with, since we know what quadratics do. So let me go back to model 3A, which is example 6 on page 7 here, and pick up almost where we left off a little before. So this model is fixed quadratic, random linear, meaning people get their own linear rates of change, but they do not yet get their own quadratic rates of change. Do you remember our letters? What kind of variance lives in the R matrix? Residual, which is level 1, yes. Which is within or between? Within, which is inter or intra. Intra, yes. That must mean that what kind of variance lives in the G matrix? Level 2, between, inter. How many kinds of level 2 between inter variances do I have in this model? Translation. How many rows and columns in my G matrix? 2. Yes, not tricking you, I swear. I'm not going to do that to you. That would just be mean if I'm encouraging audience participation and I'm trying to trick you to do it. So no. So said differently, I'm deliberately trying to get you to think of it this as, and in as many dimensions as possible here. How many ways do people differ from each other according to this model? 2. What are they? Intercept, which means what? Where they start, and why is it where they start as opposed to where they end or any other place? Because that's where we put time 0. So intercepts are context specific. They are defined by you. They are defined by where your predictors are centered at 0. So yes, the intercept is where you are predicted to start. That's one way people differ from each other. How else do they differ? Change differently. What kind of change, more specifically? Linear change right now. Yes, they're not quadratic change yet. So do I need to talk about this as being linear differences in change at time 0? Ding. Or just linear differences in change over time, or differences in linear change over time? I got to get the words right. So, 2 alternative force choice. Individual differences in linear change, period, or individual differences in linear change at time 0. Tricky one. You think it's just over time, period. You're
throughout the time.
Throughout all the time, not just time 0? That's right. Why is that right? Time is continuous in this case. Ding, that's why, because people don't have their own quadratics yet. This is the highest order term on the random side. So linear is above intercept. That's why intercept is conditional on time 0, but linear is the highest order term right now, so it is unconditional, it is marginal on the random side. So sides are important. This model is asymmetric. On the mean side, with respect to the fixed effects, I have a quadratic which is superordinate to the linear. So this linear time slope is specific to time 0 because of this on top of it. On the random side, that is not the case. So people differ from each other in intercept, which means where they're predicted to start, and their linear rates of change. If I try to put these two matrices back together again, I wrap G into a Z matrix that makes it the right dimensionality, what do I get? When you put G and R back together again? V for victory. Yes. So what does V tell us? What is that? Besides one of your homework questions. We don't know what V is telling us? You just told me it's between and within put back together again, otherwise known as your total data prediction. So you have 6 occasions in this example. What is row 1, column 1 of V? Not a mean. Other word. Not average. It's on the other side of the model. It's a variance. This is what our model says the variance at time 1 is supposed to be. It's a combination of 3 things: between person intercept differences, between person linear slope differences, and residual differences, people's deviations from their own line at time 1. So row 2, column 2 is what? What is it telling us? Variance at session 2, yeah. So this is what the model is saying your data are supposed to be distributed like. This is the prediction. And how would I know what that right answer is? Is it possible to get a right answer for what V should be? I heard it. Unstructured, yes. We can build an unstructured version of V just using R or using G and R, but yeah, that's the answer key. So that's the comparison model. When can't I have an unstructured answer key though? Unbalanced data, indeed. All right. So here's my fixed effects. How many rows are in this solution for fixed effects table? 3, yes, say it with authority, people. That means I have how many fixed effects in my model? 3, hooray. Likewise, it's split across 2 pages. Let me put it back together again. How many rows are in my covariance parameter estimates table that are currently highlighted in front of you? 4. So how many parameters are in my model for the variance? 4. Yes. When in doubt, count. I'm deliberately trying to show this to you because this has always been a sticking point. Kids get confused about how many parameters are in a model. You can always count. So model for the variance, how many rows are in this covariance parameter estimates table? Model for the means, how many rows are in this solution for fixed effects table? So my model then says predicted outcome at session 1, which is time 0, is 1945 milliseconds. What happens to that predicted mean as time goes on? It decreases. Does it decrease more as time goes on or less? What do these two together do to it? Decreases more or decreases less? Less because they're different signs, yes. So initially, instantaneously at session 1, the linear slope is minus 120. It becomes, which of the four is this? Less negative by how much, and don't say 13? Yeah, 26-ish, whatever 13 times 2 is. Twice the quadratic is how the linear slope changes per unit time. So the estimate statements then help convey what the model is actually saying happens on average. These are the trajectories, or excuse me, these are the predicted means from the trajectory. And the bottom part here, these are the expected linear slopes at each occasion. And apparently I accidentally deleted the other half of this p-value. I'll have to look back and see what that was, but I think it's still non-significant. So minus 120 at the first occasion is the linear slope at that occasion. The linear slope becomes less negative by about 26 as each additional occasion passes. And we also get a standard error. A couple things I want to point out here. The standard errors are the smallest in the middle because that's really where the most information is. Those slopes are well anchored because they're towards the center. The other thing I want to point out is that this could be useful as a diagnostic to the extent that the model is right. At what point do you think more practice doesn't help? Yeah. So I would say somewhere between 4 and 5, right? After that, the linear slope is non-significant, and it actually starts heading back up, and that's predicted by the quadratic. Effect size for that, it explained 6% more of the residual variance that remained at this point. By the way, the ncov equals 4 in this macro is referring explicitly to how many rows are in your covariance parameter estimates table. That's just to make the macro work a little bit more efficiently. All right. So random quadratic, allowing each person to have their own rate of acceleration or deceleration. If I allow random quadratic slopes, how many terms have I added? And don't say 1. And don't say 2. It's 3. Do you remember the rule? The number of words on your random statement is the number of things you've just added. Because not only did I add the random quadratic variance, I added its covariance with the intercept and its covariance with the linear slope. So that's degrees of freedom equals 3. So our matrix is still within person level 1 residual variance. G matrix is still between person level 2 variance. How many ways do people now get to differ from each other? 3. They get to differ from each other in their intercepts, which is still their expected value at the beginning of the study. They get to differ in their linear slopes, that's 2, 2, and they get to differ in their quadratic slopes, that's 3, 3. So when I say they get to differ in their linear slopes, that number is specific to what? 25,000 and some change is the variance in linear slopes when? Times 0. Yeah, because now it's lower order with respect to the random quadratic. 634 is the variance of the quadratic slopes all the time. The quadratic is the highest order term on both sides of the model, so it is unconditional. This may not help, but I'll say it anyway. It means that the rate of change changes constantly over time. It's always 26 more, point being. Here's my new predicted V matrix for the expected variance and covariance across occasions. Here's my new covariance parameter estimates table that has 7 lines in it. What the hell is un22 again? Do you remember that? It's the coordinates of what? The random effects, the G matrix. And so what does the un part mean? It means unstructured. So the idea is that here's my G matrix. It gets to be unstructured, meaning each random effect variance and covariance gets to be whatever it wants. We're not putting any kind of constraint on it, and we never will. That's what that means. Something that I will never ask you about, but just to point out what this means. This null model likelihood ratio test, we referred to this in one instance, which was testing a model that had no random effects versus a model that had a random intercept. So we used that to test the intraclass correlation. At this point, it's a 6 degree of freedom test because what it's doing is testing the necessity of the entire G matrix. So this is saying, are there any random effects in the data? Yeah. I don't find that to be terribly informative, but it does spit out by default. Here are my random effects confidence intervals that convey the size of each of my random effects. So the interval is centered around the fixed effect for each of these, intercept, linear slope, and quadratic slope. And what goes inside the interval is 1.96 times the square root of the variance for that term. So this is intercept variance, this one is linear slope variance, this one is quadratic slope variance. Here's a question. What if I were computing these same intervals for the previous model in which I did not have a random quadratic term? How many confidence intervals would I need to make then? 2 or 3 still? Yeah, if I'd only need 2 because I'd still have these 2 variances, but I wouldn't have this one. So that's another way to think about it. If you only have a fixed quadratic, you're saying the interval is a constant. There is no interval. Everybody gets this number, the end. Since I'm adding a random effect, I'm not computing any kind of pseudo R-square. Random effects do not explain variance, they just make new piles of it. And I do a likelihood ratio test to compare the fit against the fixed quadratic random linear model. Here's my 3 degrees of freedom. Deviance difference, -2 log likelihood difference is about 38. It only needs to be about 8 to be significant, so hooray. Sure. Where did I get which numbers? Oh. I've memorized the first part of the chi-score table for alpha equals 0.05 for degrees of freedom. Yeah, 3.84 is for 1 degree of freedom, 5.99 is 2, 3 is 7.82, 4 is 9.49, and 5 is going to be on the order of 12. That's, yeah. Or just, you know, let it figure it out for you, right? But yes. Yes, back in the day before we had software that would do things or I knew how to use it, I would go to a chi-square table like in the back of your intro stats book, or you can still find people's images online of these things. So that's where it came from. All right. Other questions? So I had told you before, cubics I find rarely useful. Am I done? And how do I know if I'm done? Because at this point I've added everything that I thought I would add, and it's all significant. How do I know if it's good enough? I have balanced data, so in this case I can know. Yeah, I have the answer key model I can compare against. So we're going to do a couple of checks here to make sure that I'm really done. Check number 1 is this idea of an R matrix, which we've used the same R matrix this whole time. We've been adding random effects. Do you remember what the name for that is? VC. I would also accept diagonal as a word. VC stands for variance components, means equal residual variance across time. And what kind of covariance across time is indicated by the giant emptiness up there? None. So that structure is a testable hypothesis. What we're saying is that after giving each person their own bendy line, the residuals have equal variance and no covariance whatsoever. Well, I can test whether each aspect of that is true. Testing heterogeneity of variance in this case is somewhat problematic because allowing these residual variances to be different is going to negatively impact these variances right here. Part of the job of the random linear and quadratic slope variances is to allow different variances over time. So allowing different residual variances too is somewhat redundant. It could cause estimation problems. But this idea that the residuals might have some correlation we can certainly test. And so I'm invoking some additional material that I don't think is in Chapter 6 in the book because I put it in Chapter 5 instead. This idea of whether or not we need to allow an additional correlation in the R matrix for the residuals. So I'm going to try 2. Type equals AR1 on the repeated line here. So it's the same random quadratic model, but I'm picking up an autoregressive correlation among the residuals. Type equals UN for ever and ever amen still on the random line. So the autoregressive parameter that it estimated for my residual correlation is 0.17. That means that sessions that are 1 unit apart have a residual correlation of 0.17. Sessions that are 2 units apart have a residual correlation of 0.17 squared. 3 apart is 0.17 cubed, and so on. So that's what this term right here is referring to, my autoregressive correlation. Now this is a potential trick question, I'll tell you this. Normally, what do I say about the p-values that show up for variance-related things? No, right? Remember why? They're on the wall, right? They can't be negative, so a wall test for things on the wall is not allowed. Can a correlation be negative? It could, actually. So in this case, I would say, you know what? You could probably look at that. It's probably okay. However, if you want to cover your bases, likelihood ratio test is still likely to be more correct, but in this case, they agree. So if I stare at the wall test, p-value for that new autoregressive correlation is 0.18. P-value is 0.15 if I do the model comparison. So either way, the fact that the model comparison is non-significant or the correlation is non-significant means what? Do I need it? Nah. So I'll try one more just to make sure. A lag1 toplets, excuse me. I'm going to mispronounce that forever, I think. So top2 creates a pattern that looks like this, where the diagonal is the residual variance, and then I'm allowing an additional residual covariance for sessions that are 1 unit in time apart. That translates into a correlation of 0.12. And the rest of it is empty. That correlation of 0.12, similarly non-significant. Model comparison agrees in this case, so yeah. So I'd say I tried, the R matrix seems like it's okay. When in doubt, stare at pictures. So the top panel here, the solid squares is the answer key. Saturated means possible when you have balanced data. The straight line with the triangles is what the linear model says. The bendy line with the diamonds is what the quadratic model says. And I have deliberately extended the predictions past the data so that you can get a sense of what it says should happen. So theoretically, neither one of these models makes me very happy. Linear says people are going to keep getting better and better and better, and eventually they'll have a negative response time. They'll be so good. They'll get done before they even started. Yeah. And quadratic says they're going to do what? Yeah, they'll get better and then they'll start sucking all of a sudden. Now that's possible if they like hate your task and they don't want to do it anymore, but that's a whole separate phenomenon. So I'm not really happy with either of these from a theoretical perspective. From a data fit perspective, the bendy line fits better, but you can see that it still has some misfit down here. So how do we know if it's good enough? We need some kind of model comparison. Can I do a likelihood ratio test against the saturated means model versus the quadratic model? In theory, yes, so long as what is true. What kind of estimator would I be in if I could do that? That's ML. Am I in ML right now? No. I'm in REML, and I'm in REML, and I'm going to stay there because I don't have very many people, 100 people or so, right at the edge where it's going to matter. So how do I get that same idea, but in REML? This isn't in the book either. It's on my list of things that I'm going to put in the next version if I ever get to make one. Here's how you can do it. So we'll go to the next page and then we'll come back to the variance model here in just a second. So here is my best model so far, random quadratic. I want to know if that bendy line that it predicts adequately captures the saturated means. If I can't do a -2 log likelihood comparison, what I can do is put in enough extra parameters to create a saturated means model and then test the significance of those extra parameters. Now this is going to look a little crazy, but what I've added here, I have underlined. I have added a fixed effect of session back in the model. Session is being treated as a categorical predictor by SAS, meaning it's making dummy codes for it. Because I'm letting SAS make the dummy codes for it, I'm letting it figure out how many it needs. And that's why you end up with this table of fixed effects, which I will tell you is largely uninterpretable. I could do it, but it isn't worth the time that it would take. What I want to point out is how many rows do we now have in that table that have numbers in them? 6. How many means do I have? 6. I have backwards engineered my way into a saturated means model. So what I want to do then is see, are those extra 3 effects that it just used to try and fill in the gaps, are those as a set significant? That information is given to me automatically as a multivariate wald test in the type 3 test of fixed effects box. So in your last homework, and I think maybe even in this one, I asked you for the test statistic as to whether there are mean differences across time, right? That's normally where you would see this. This is telling you, are there still mean differences across time after controlling for the fixed quadratic? In other words, is the fixed quadratic accounting for the mean differences? If it is, I shouldn't need those extra 3 parameters. They should be fully redundant. As it were, though, p equals 0.03. So that means that my fixed quadratic bendy line is not adequately reproducing the means. Otherwise, these extra deviations would all be 0. Charlie? Nope. Doesn't matter. It's just going to plug holes, and the rest of the parameters will rearrange themselves to accommodate. The key idea is that you've saturated the model. You have 6 things in to explain your 6 means. So this is as good as it gets. Yeah, it's not going to tell you where the misfit is per se. This is just going to tell you that there is misfit. So you'd have to look then, and this is where pictures are indispensable to try and figure out where the quadratic is missing and what you could do instead. And in this case, it's too steep, or excuse me, it's not steep enough here, and it's too steep here. So this is one way you can get at the idea of absolute fit on each side of the model separately, so that it can be used for diagnostic purposes. On the other side, though, let's look at the variances. The bottom panel shows the predicted variance by each of our models. Saturated means, again, solid line with the squares. So variance is decreasing across sessions. People are becoming more homogeneous after more practice. The random intercept model is the one that's flat. It says that people stay the same, right? Everybody changes the same. That means they can't spread out. Random linear is the one that looks like a U shape because a random linear slope generates a quadratically changing pattern of variance. And the one that goes crazy is the random quadratic. It has a quartic dependency on time. I didn't plot all the covariances, but you could imagine what those may look like. On this case, though, we can do a -2 log likelihood comparison. So we can do unstructured R matrix versus random quadratic. And the key idea here, though, is we're keeping the mean side the same. So we're only testing the variance side. The difference is 14 degrees of freedom. So the unstructured model has 14 more terms in it than the random quadratic, and those 14 as a set do effectively plug the holes that the random quadratic left behind. So big picture, quadratic is probably the best I could do within this family of polynomials, but it's not good enough. And I don't like it, so there's that. Theoretically unmotivated. That's why I don't like it, by the way. Questions on that? And that's everything that would be in your homework. I didn't ask you to do absolute fit tests in this homework, but I'm going to ask for them in the next homework, which will be on piecewise slope models. So we can talk about those. So changing gears to a new family of models. You're going to like these, I promise. These are way more fun. Piecewise models. These are also known as linear splines. Interrupted time series is another word that I've heard recently describe these things. This is the idea that time is unfolding for reasons that are under some sort of knowledge or control, and you can specify your model for change to take into account that. So here is a real data plot from a student in my class at Nebraska several years ago. She had a multiple baseline intervention trying to improve kids' behavior, where kids are supposed to do more of whatever it is, I think, ask questions or read words or, something. And so they measured the kids several times, just watching them do their thing, nothing happened. They introduced their new intervention designed to make them want to do this behavior more, and lo and behold, they jumped up and they kept getting better and better, and then they took it away, and then they started sucking again, and they came back down, and then they brought it back, and then they went up. So fairly powerful within subject evidence for that whatever they were doing was effective, because when they took it away, they went back down, and then they brought it back. So if you thought about this trajectory as a continuous trajectory, what order of polynomial would you need to fit this, right? It'd be like linear to quadratic to cubic to quartic to like a seventh order polynomial to capture all of this, like the worm, right? Yes, once upon a time I could do the actual worm on the floor, but I will spare you that because I think I'd probably just hurt myself today, but we'll just... So yeah, and furthermore, an eighth order polynomial wouldn't actually answer her research hypothesis. Like, did kids get better because of what we did, right? It's a fairly simple question. So what I helped her do, and what I hope they eventually went off and did, is to fit a piecewise slopes model where they broke time into sections and they fit one linear slope during each epoch of the design. And they also put in shifts and intercept, which I call jumps in the text, basically the acute difference before and after. And they can test whether the slope differs between phases as well as whether the intercept differs between phases. That directly answers their question as to whether what they were doing changed behavior. So these types of models are very, very useful for intervention type studies where you know what happened. Either you did it or you know when it happened. Some other real world examples, like before and after a hurricane, those kinds of things where you know when it hit and you have measures before and after something happened. I've seen these sorts of models used in like stress reactivity. So I had a student also who had 3 observations with moms and babies where they brought the baby into the lab and it was like baseline and all fine, and then they made the baby mad. Like they pinned its arms down or they took its toy away and like let baby freak out like, ah! Measured cortisol and amylase, again, as I did at baseline. And then they gave the baby back to the parent and everything's all cool. And then they measured the 3rd time. Yes, the IRB approved this, apparently. IRBs will approve lots of interesting things, I guess, if you word it carefully. But in this case, it wasn't child abuse because this all transpired over the span of like 5 minutes or something. And so she was interested in the reaction to the stressor, which she called this slope from okay baby to freak out baby reactivity, I guess this way for you guys. And the other one she called responsivity, I think it was, something like, the idea of being able to come back down. And so the idea that she had these 2 slopes more directly mapped onto her ideas of the processes that were involved than would a quadratic, which would fit the same 3 occasions perfectly. Now, where's the downside? If you have 3 occasions, how many random slopes per time do you get to have with 3 occasions? Remember the rule? N minus 2, how many random slopes she gets? She gets 1. So either responsivity or reactivity could be random, but not both. Had she had a midpoint observation on each slope, that would have been infinitely better, but I did not design that study, so I couldn't help post hoc. But yes, anytime you have something going on where you know the before and the after, these models can be very useful. That brings up a question I got once. What about like something before and after puberty? that seems like a valid point, but I asked the person, okay, so you have the date in the data set, right, when puberty happened. That's what you would need to have to pull this off. There is a whole nother family of models designed to find the point at which the trajectory changes. Those are called latent change point models. I'm not going to cover those, but I can point you towards resources if you're interested in them. I will tell you it takes a shit ton of individual data to estimate that, like shit tons. Because in order to find a random change point, you have to have a really good idea of what people's slopes would be before and after. But those types of models can be effective if you want to know sort of at what point it looks like something shifts. And they're used in things like terminal decline and aging, like at what point do you sort of fall off the cliff, or in other kinds of disease progressions where you're not quite sure when things start to get really good or really bad. So, piecewise models, my friends. So here's an example with cortisol also. This highlights two things actually. Number one, that you can do these models even if you don't have balanced time. So in this case, they had 4 observations a day, where one was defined as just whenever you woke up, and that could be 6 a.m. or it could be 10 a.m. 30 minutes later, which is when cortisol is supposed to peak for the day, and then we had a second slope that captured this afternoon decline. But when you look at the prediction relative to this curve, do you see anything potentially amiss here? Does that fit? Do you have any ideas on how I could make it fit better? Kind of bendy, yeah. I could add a quadratic slope to try and make this afternoon part bendy. So even though these are known as like piecewise linear slopes a lot of the time, they don't have to be linear. Each part can be whatever form it needs to be to go with the data. So if I were to write a 2-slope model, where I just have the linear part for simplicity here, it would look remarkably similar to the equation for the random quadratic. The only difference is in the time variables that are being defined in level 1. Previously, it was time and time squared. Now I'm going to have a first slope and a second slope. In each case, though, the intercept is still where the time variables are at 0. I have a fixed part in red and a random part in blue. I have a fixed slope for the first slope and a random slope, and a fixed slope for the second and a random slope. And I would need 4 occasions to fit this model because it has 2 random slopes in it. So I'm going to use our example data to show you an atheoretical version of a piecewise model that fits surprisingly well. Quadratic didn't work, so I'm going to try this. I'm going to do a piecewise slope model where the knot, the point where the slopes change, is at the second occasion. Now, just based on the idea that I've got 2 points and 1 line here, how well do you think the first slope's going to fit? Perfectly, yeah. How well is the second slope going to fit? Imperfectly. So I can actually test both these fixed effects and random effects for them. I can have a random slope for the first part because this part down here is not going to be perfect. It works out that you have enough information to pull it off. So I'm going to do a 2-slope model on our response time data. Now, how to set up the codes. There are 2 ways to set up these piecewise models. One way may be more useful to you in a given situation. I'm going to show you both so that you know how to do it. The most direct way, as I call it here, 2 direct slopes. You estimate the rate of change during each epoch separately. So I'm going to create 2 variables, one that indexes the change from session 1 to 2, and another that indexes the change from session 2 to 6, and that's why I've named them like that. So note the pattern of the codes. The first variable goes from 0 to 1, and then it shuts off. By keeping a value of 1 for the rest of the occasions, it effectively shuts off. so that it is only indexing the change between 1 and 2. The purple variable, slope26, picks up where it left off. So then it starts here, goes from 0 to 1, and then it continues going. So I've tried to show via the dotted lines up here what the model would predict if the other variable wasn't included. So without the purple part, the orange model would just predict that change over time stops. And without the orange part, the purple would predict that there is no change until session 3. When you put them together, that's where you get the interpretation of specifically the change from time 1 to time 2, and that's it, and then the change from 2 to 6, both of these being linear slopes. How do I know where my intercept is? Not a trick. Same rule as before. Time 0, right? So when you're setting up these codes, keep that in mind. You have to have one place where they're both 0 for this to work. So the intercept is at session 1. Here's a quiz for you. What if I wanted my intercept to be at the not? So if I have my session 1, 2, 3, 4, 5, 6, slope 1, 2, slope 2, 6. If I wanted the intercept to be in this column right here, I put my zeros here. Let's just make the whole thing centered. There. What goes here? Can't be 1 because that would imply a change. This slope 1, 2 is supposed to have shut off by now. Goes 0. What goes here? -1. Very good. Yes. Time is moving forward still. What goes here? 0. What goes here? 1. Yes. So that's how you would set it up if you wanted your intercept at the breakpoint. It's up to you. If you have unbalanced time, you can't use these integers. You'd have to do subtraction. You'd have to have variables in your data set as to when time 1 was and when time 2 was, and then you would create your slopes via subtraction instead. There's an example in the online materials for how to do that. So let's have an example. Here's my Sas coding. There are more efficient ways to set it up, but I picked the way that would be the most transparent. If session is 1, then make my 2 variables. If session is 2, then make them this way, and so on. And you note that instead of going across, I'm going down, but the pattern of codes is the same. So my intercept is session 1, just as it was in the previous model. Slope 1, 2 tracks the change between 1 and 2, and slope 2, 6 tracks the change between 2 and 6 per session. So I'm starting with a model in which both slopes are in here as fixed effects because otherwise it doesn't really make sense. They're designed to work together. And I'm starting with a random intercept only, and then we'll test whether or not each fixed slope needs a random slope to go with it. So we're back to a random intercept only model. Slope 1, 2, and slope 2, 6 are my fixed effects, and I'm asking for predicted values at each occasion. And note the values that I'm plugging in are the ones that show up in my coding here. So what value does slope 1, 2 take on, for instance, if I'm talking about time equals 5? It's still 1. If I'm talking about time equals 5, slope 2, 6 takes on a 4. So you plug in whatever numbers go into the time coding that you use to create these slopes. So there's my R matrix, there's my G matrix, there's my compound symmetry V matrix, and here are my estimates. So how many fixed effects in this model? 3, yes. So my intercept is my expected mean at session 1, right? Time, that's when both of my slopes are 0. Slope 1, 2, and slope 2, 6. First off, are they significant? Yes, I can just stare at this p-value because they're not on the wall. A null hypothesis of 0 is fine. So minus 163, someone want to throw that in a sentence for me, please? Let's call on the back. Scott. Want to throw the 163 in a sentence for me, please? Mm-hmm. Go for it. Don't be afraid. It's just a slope. It's just a slope. For every 1 unit, more session, right? 1 unit change in time. What happens? It's negative, so what happens? Response time is our dV. Response time is our dV. Goes up or down? Goes down by how much? 163. There you go. It's in the sentence. Yes. So that's my rate of change between slope 1 and 2 specifically. Since there's only 1 unit time difference, you can just call that the difference. People are predicted to improve by 163 milliseconds between session 1 and 2. The end. Significantly improve. Throw that in there. After that, are people still improving? On average, sure. By how much? 33-ish milliseconds. 2 more words I need. Is it 33 milliseconds between session 2 and 6? Per session. This is a slope, exactly. So the rate of change between sessions 2 and 6 is 33 milliseconds a session. That's significant. Now I'm going to stare at those numbers. Do you think that 32 looks bigger, or excuse me, negative 32 looks bigger than negative 163? What do you think? Do those rates of change look different to you? Can you think of a way that we would find out? Could we just ask Sas? Hey Sas. And it'll pop up, yes, how can I help? Is minus 163 different than minus 32? And it would say, writing your estimate statement. And it would pop this up on your display. So when you have a negative number in an estimate statement, that's asking for subtraction. The slope words refer to their fixed effects, remember? So I'm literally asking it to find me the difference of 163 and 32. And not only will it find the difference, it will find me the standard error of that difference and the p-value for that standard error. Survey says, there it is. 163 minus 33 is 130. 130 is not 0. If I take these predicted intercepts at each session and I plot them against my original means, lo and behold, that's my blue line here. How'd I do? Pretty damn good. So yes, because this line isn't perfect, this part isn't going to be perfect either. And that allows us to have a random slope potentially. So the rate of change is, how would I talk about this in words? What happens to the rate of change over time? Yeah? So initially, what happens to people? They improve. Later on, what happens to them? Improvement reduces, or I would also go less negative, right? Improvement diminishes, something like that. Throw in your GRE words. And we know that the rate of improvement differs later on significantly by 130. It is 130 less negative. That's the extra piece right here. Ta-da! Which variance component should have been explained by my two slopes? Residual or random intercept? Are slopes time things or people things? Time things. Is it residual or random intercept? Residual, yeah, and there it is. 24% of the residual variance is explained by my piecewise slopes. Ta-da. Questions? All right, then we will pick this up on Wednesday. Office hours start now. Happy Halloween.